A galaxy doesn't just sit still in space, it moves. And our galaxy, the Milky Way, is racing through the cosmos at over 2 million kilometers per hour. That's fast enough to cross the distance from Earth to the Moon in less than 12 minutes. But here's what makes astronomers uncomfortable. We're not drifting aimlessly. We're being pulled towards something massive, something we cannot see. And the closer we get, the faster we're moving. This isn't speculation. It's measurement. Decades of careful observation have revealed that an enormous gravitational anomaly exists in the direction of the constellations Centaurus and Hydra, a region of space so far away that light from it takes hundreds of millions of years to reach us. Scientists call it the Great Attractor, and it's dragging our galaxy, along with thousands of others, toward a destiny we're only beginning to understand. If you're curious about what lies ahead in the darkness, and why the universe refuses to let us see it clearly, subscribe now, hit that like button, and let's explore this cosmic mystery together. To understand why the Great Attractor is so unsettling, we first need to grasp just how strange galactic motion really is. When you look up at the night sky, everything appears frozen. The stars hold their positions. Constellations remain recognizable across generations. The moon traces its familiar path. This stillness is an illusion. Everything in the universe is in motion, and that motion operates on scales that resist human intuition. Earth spins on its axis at over 1,600 kilometers per hour at the equator. We orbit the sun at roughly 100,000 kilometers per hour. The sun itself isn't stationary either. It carries our entire solar system around the center of the Milky Way at more than 800,000 kilometers per hour. A complete orbit takes about 230 million years. Dinosaurs roamed Earth the last time we were in this part of the galaxy. But even this orbital motion is just one layer. The Milky Way as a whole is moving through space, not rotating, not orbiting anything visible, but traveling in a specific direction at immense speed. This motion was discovered not by seeing the galaxy move, but by measuring how light from distant objects behaves as we approach or recede from them. When an object moves toward you, the light it emits gets compressed, shifting toward the blue end of the spectrum. When it moves away, the light stretches, shifting toward red. This effect, called the Doppler shift, applies to sound as well. A siren approaching you sounds higher in pitch than one moving away. Light does the same thing, and astronomers use this property to measure cosmic velocities with extraordinary precision. In the early 20th century, astronomers noticed something unexpected. Most galaxies showed red-shifted light, meaning they were moving away from us. This observation led to the discovery that the universe itself is expanding. Space stretches, carrying galaxies apart like dots on an inflating balloon. This expansion is not motion through space. It's the expansion of space itself. Galaxies aren't fleeing from us. The fabric of reality is growing, and they're being carried along. But some galaxies didn't follow this pattern. A few showed blue shifts, meaning they were approaching us. Andromeda, our nearest large galactic neighbor, is moving toward the Milky Way at about 110 kilometers per second. In a few billion years, the two galaxies will collide, merge, and form a new structure. This motion is local. Gravity binds the Milky Way and Andromeda together in what astronomers call the local group, a cluster of more than 50 galaxies held by mutual attraction. Within this group, individual galaxies can move toward one another even as the universe expands around them. But when astronomers corrected for cosmic expansion and measured the Milky Way's motion relative to the broader universe, they found something strange. The galaxy wasn't just moving. It was being pulled. After accounting for the sun's orbit around the galactic center and Earth's motion around the sun, measurements revealed that our galaxy is traveling at roughly 600 kilometers per second in a specific direction. That speed is extraordinary. It's over 2 million kilometers per hour. At that velocity, you could cross the width of the United States in less than 2 seconds. Yet this motion goes almost unnoticed in daily life because everything around us, our solar system, nearby stars, the entire galaxy, is moving together. There's no relative motion to feel. What's particularly striking about this discovery is how it was made. Astronomers couldn't simply look at the Milky Way from outside and watch it move. We're inside it, embedded within its structure, with no external reference point. Instead, they had to use the cosmic microwave background. the afterglow of the Big Bang as a fixed reference frame. This radiation fills all of space uniformly, and by measuring how its temperature varies slightly in different directions, astronomers detected our motion through it. The pattern is called a dipole. The radiation appears slightly warmer in the direction we're moving toward and slightly cooler in the direction we're moving away from. This temperature difference is tiny, only a few millikelvins, but it's measurable, and it revealed something profound. We're not at rest with respect to the universe. We're moving through it, swept along by forces that operate on scales far larger than our galaxy, far larger than our local group, far larger than anything we'd previously imagined. This motion is not something we chose or created. It's something the universe imposed on us through its large-scale structure, through the distribution of matter and dark matter that formed over billions of years. And that structure is pulling us relentlessly towards something we cannot fully observe. What makes this motion so peculiar is that it's not random. The Milky Way isn't wandering. It's heading somewhere, and when astronomers traced that direction back, they found no obvious cause. No massive galaxy cluster sat in our path, exerting a clear gravitational pull. No superstructure appeared in telescopes to explain the acceleration. Instead, they found a region of space obscured by the Milky Way's own disk. We live inside a spiral galaxy, and our position within it means that a thick band of stars, gas, and dust blocks our view in certain directions. This region, called the zone of avoidance, hides whatever lies beyond it. For years, astronomers suspected that something massive must exist in that hidden zone, something capable of pulling thousands of galaxies, including our own, across hundreds of millions of light years. But they couldn't see it. They could only measure its effects. That invisible mass became known as the Great Attractor. The name is both descriptive and eerie. It captures what the object does without explaining what it is. And for decades, that's all we had: a name, a direction, and a growing sense that the universe contains structures far larger and more influential than we'd imagined. Understanding the Great Attractor required patience, better instruments, and a willingness to look at the universe in ways light alone couldn't reveal. The problem wasn't just that we couldn't see the Great Attractor directly. The problem was that our galaxy was in the way. The Milky Way is a flat, rotating disk of stars, roughly 100,000 light years across. We sit about 2/3 of the way out from the center, embedded in one of the spiral arms. This position gives us a clear view perpendicular to the galactic plane. We can see deep into intergalactic space above and below us. But when we look toward the galactic center, or directly through the disk, our view is blocked by immense clouds of gas and dust. These clouds are opaque to visible light. Starlight scatters and absorbs before it reaches us, turning distant objects into faint smudges, or erasing them entirely. This is why the Milky Way appears as a glowing band across the night sky. We're seeing the combined light of billions of stars in the disk, but we can't resolve individual objects beyond a certain distance. Anything behind that veil is invisible to optical telescopes. The Great Attractor sits in precisely this region. Its position in the sky places it directly behind the densest part of the Milky Way's disk, hidden in the zone of avoidance. For years, astronomers knew something massive was pulling us but couldn't observe it. It was like hearing footsteps in a dark room without being able to turn on the light. This limitation forced scientists to develop indirect methods. If visible light couldn't penetrate the dust, other wavelengths might. Radio waves, for instance, pass through cosmic dust with little interference. By mapping radio emissions from hydrogen gas, astronomers could detect galaxies even when starlight was blocked. Infrared light also penetrates dust better than visible wavelengths. As technology improved, infrared telescopes began revealing structures in the zone of avoidance that optical instruments missed. Slowly, a picture began to emerge. In the 1980s, astronomers using redshift surveys mapped the large-scale structure of the universe. By measuring how fast galaxies were receding due to cosmic expansion, they could estimate distances and build three-dimensional maps of galactic distribution. These surveys revealed that galaxies aren't scattered randomly. They cluster together in groups. Those groups form superclusters, and superclusters arrange themselves along vast filaments separated by enormous voids. The universe resembles a cosmic web, with matter concentrated along threads and nodes, while emptiness dominates the volume. Within this structure, the Milky Way belongs to the local group, which in turn is part of a larger structure called the Laniakea supercluster. Laniakea spans 500 million light-years and contains roughly 100,000 galaxies. It's not held together by gravity in the way a galaxy cluster is. Instead, it represents a region of space where galaxies share a common motion, all flowing toward a central point. That central point is the Great Attractor. But even this discovery didn't fully explain the motion. When astronomers calculated the mass required to produce the observed gravitational pull, they realized the Great Attractor alone wasn't enough. Something even larger had to exist beyond it. Measurements showed that galaxies in Laniakea weren't just moving toward the Great Attractor. They were being pulled past it, toward an even more distant and more massive structure. This raised a troubling question. If the Great Attractor was invisible because of the zone of avoidance, and something beyond it was influencing our motion, how could we ever hope to see what was really out there? The answer came from combining different observational techniques. Infrared surveys began to map galaxies in the hidden zone. Radio telescopes detected hydrogen clouds that traced large-scale structure. X-ray observatories identified hot gas in galaxy clusters, revealing mass concentrations invisible to other instruments. Slowly, piece by piece, the veil began to lift. What emerged was both familiar and alien. The Great Attractor wasn't a single object. It was a region of space dense with galaxy clusters, all gravitationally bound and collectively exerting an enormous pull. But it was only part of a much larger structure. Beyond the Great Attractor, hundreds of millions of light-years away, lies an even more massive concentration of galaxies, known as the Shapley supercluster. This structure contains over 8,000 galaxies and represents one of the densest regions of matter in the observable universe. Its gravitational influence extends across unimaginable distances, affecting the motion of everything within hundreds of millions of light-years. The Milky Way is being pulled not just by the Great Attractor, but by the Shapley supercluster beyond it. Our galaxy is falling toward a destination so distant that even at 2 million kilometers per hour, we won't reach it for billions of years. And by the time we do, the universe's expansion will have carried it even farther away. This realization shifted our understanding of cosmic motion. Galaxies aren't just drifting. They're flowing along gravitational rivers carved by the largest structures in existence. These flows shape the universe's architecture, determining where matter accumulates and where voids expand. We are not passive observers. We are participants, caught in currents far older and far larger than anything human civilization has witnessed. Yet even with better maps and clearer data, fundamental mysteries remain. Why is the Shapley supercluster so massive? What processes concentrated so much matter in one region of space? And are there even larger structures beyond it, pulling on Shapley the way Shapley pulls on us? These questions push against the limits of what we can observe. Light has a finite speed, and the universe has a finite age. There are regions of space so distant that their light hasn't had time to reach us yet. Beyond the observable universe lies everything we cannot see, and within that unknown expanse, structures may exist that dwarf even the Shapley supercluster. We can measure their effects indirectly, but we may never see them directly. The Great Attractor forced astronomers to confront an uncomfortable truth. The universe is not transparent. It hides things from us, not out of malice, but simply because of distance, dust, and the limitations of light. To understand where we're going, we had to learn how to see in the dark, and what we found was both smaller and larger than expected. Smaller because the Great Attractor itself was not a single anomaly, but a collection of known structures. Larger because those structures were only waypoints in a journey, shaped by forces operating on scales almost beyond comprehension. The discovery of the Great Attractor and the Shapley supercluster revealed something profound about the universe's structure. Matter is not distributed evenly. It clumps, clusters, and organizes itself into hierarchies that span billions of light years, and the forces driving this organization are still pulling us forward, accelerating our galaxy toward a fate written into the fabric of space-time itself. But understanding that we're being pulled is only the beginning. The real question is what happens when you start moving that fast, and whether the journey itself changes what we are. When a galaxy moves through space at over 2 million kilometers per hour, it doesn't travel alone. It carries everything with it: stars, planets, gas clouds, dark matter, and the invisible framework that holds it all together. But motion on this scale introduces forces and interactions that reshape galaxies over time, sometimes violently. These effects are not immediate. They unfold over millions or billions of years. But they are inevitable, and they leave marks that astronomers can read like scars. One of the most significant effects comes from something called ram pressure. As a galaxy moves through intergalactic space, it encounters a thin but pervasive medium of gas. This gas is extraordinarily diffuse, far thinner than the best vacuum we can create on Earth. But when a galaxy plows through it at hundreds of kilometers per second, that gas pushes back. The pressure strips material from the galaxy's outer regions, particularly hydrogen gas that fuels star formation. This process, called ram pressure stripping, can fundamentally alter a galaxy's structure. Star formation slows or stops. The galaxy becomes quenched, its bright spiral arms fading as fewer young stars are born to replace aging ones. Over time, a vibrant spiral galaxy can transform into a dim, reddish elliptical, its reserves of raw material exhausted by the journey. The Milky Way is not yet experiencing significant ram pressure stripping, but as we continue toward the Great Attractor and the Shapley supercluster, this process will intensify. The intergalactic medium becomes denser near massive galaxy clusters. When we eventually enter those regions, the Milky Way will begin to lose gas from its outer disk. Star formation will decline. The galaxy's appearance will change. Then there are gravitational interactions. As galaxies move through regions of high density, they pass close to other galaxies. Gravity doesn't require contact. It operates across vast distances, and even a near miss can warp a galaxy's structure. Spiral arms can be distorted. Stars can be flung outward in tidal streams. In extreme cases, galaxies merge, their structures collapsing into one another, triggering bursts of star formation as gas clouds collide and compress. The Milky Way is already on a collision course with Andromeda. That encounter, expected in about 4 billion years, will reshape both galaxies entirely. But that's a local event. The larger motion toward the Great Attractor introduces the possibility of additional interactions over even longer timescales. As we approach denser regions of space, the probability of close encounters increases. Each one will leave its mark. Another subtler effect comes from dark matter. Galaxies are embedded in massive halos of dark matter, invisible substance that makes up most of the universe's mass. These halos extend far beyond the visible galaxy, and as galaxies move through space, their dark matter halos interact gravitationally. These interactions can transfer momentum, alter trajectories, and even strip dark matter away from smaller galaxies. The Milky Way's dark matter halo is likely being shaped by our motion right now. As we fall toward the Great Attractor, we're not just moving through empty space. We're moving through an ocean of dark matter whose distribution reflects the same large-scale structures pulling us forward. This invisible scaffolding influences our path in ways we're still learning to measure. Then there's the question of what happens when we arrive. The Great Attractor is not a destination in the traditional sense. It's not a single object with a defined surface. It's a region of space dense with galaxies, each one orbiting a common center of mass. When the Milky Way eventually enters this region, it won't stop. It will begin orbiting along with everything else, bound by gravity into a vast chaotic dance. Over billions of years, galaxies within such clusters tend to merge. Collisions are inevitable when thousands of galaxies occupy the same region of space. The Milky Way's ultimate fate, assuming it survives long enough, may be to merge with other galaxies in the Great Attractor, forming a single enormous elliptical galaxy. This process is already underway elsewhere in the universe. We can see ancient galaxy clusters where mergers have produced giant ellipticals, galaxies so massive and old that they dominate their surroundings. But there's a catch. The universe is expanding, and not just expanding, accelerating. This acceleration, driven by a mysterious component called dark energy, pushes space apart faster than gravity can pull it together. On small scales, gravity wins. Galaxies within clusters remain bound. But on larger scales, cosmic expansion dominates. Structures that aren't already gravitationally linked will never meet. They'll drift apart faster than light can travel between them. This creates a strange paradox. The Milky Way is being pulled toward the Great Attractor and the Shapley Supercluster. We're accelerating toward them, but the universe's expansion is also accelerating. Whether we ever truly arrive depends on a cosmic race between gravity and dark energy, between the pull of mass and the push of space itself. Current measurements suggest that we will eventually reach the Great Attractor. We're close enough and moving fast enough that gravity has already won the local battle. But the Shapley Supercluster, farther away, may be a different story. Even as we're pulled toward it, cosmic expansion may carry it away faster than we can approach. We could spend eternity chasing a destination that recedes faster than we can travel. This realization is humbling. The universe's expansion doesn't just limit how far we can see, it limits where we can go. Even with motion measured in millions of kilometers per hour, most of the universe will remain forever beyond our reach. The galaxies we observe today in the distant cosmos will fade from view as expansion stretches the space between us. Their light will redshift into invisibility. Future civilizations, if they arise billions of years from now, will look out and see a lonelier universe. Fewer galaxies, darker skies, less evidence that anything exists beyond their local cluster. They'll have to trust the records we leave behind or rediscover cosmology from scratch with diminished data. Our motion toward the Great Attractor is not just a journey through space, it's a race against time, a struggle between the forces that bind structures together and the expansion that tears them apart. And it's a reminder that the universe does not wait for us. It moves, changes, and evolves on timescales that make human history look like a brief flicker. Yet this motion also connects us to something larger. The same forces pulling the Milky Way shaped the universe's structure from its earliest moments. The same gravitational flows that carry us forward today were set in motion billions of years ago, sculpted by fluctuations in the density of matter that emerged shortly after the Big Bang. We are not just moving. We are tracing a path written into the cosmos itself. Understanding that path requires looking backward to the very beginning, when the universe was young, uniform, and far simpler than it is today. And that's where the story takes an even stranger turn. Because the forces pulling us forward didn't arise randomly. They emerged from the universe's initial conditions, amplified over billions of years by gravity's patient work. To truly grasp how gravity builds structures like the Great Attractor, we need to understand what gravity is at its most fundamental level. Most people think of gravity as a force, something that pulls objects together across empty space. Newton described it that way, and for centuries that picture worked remarkably well. It predicted planetary orbits, explained tides, and allowed us to navigate the solar system with precision. But Einstein revealed that this picture was incomplete. Gravity is not a force in the traditional sense. It's a consequence of geometry, a distortion of the fabric of space-time itself. Massive objects don't pull on each other across empty space. They warp the space around them, and other objects follow the curves that warping creates. This is general relativity, and it fundamentally changed how we understand the universe. In Einstein's framework, space-time is like a vast, flexible sheet. When you place a massive object on it, the sheet bends. A planet orbits a star not because the star is pulling it, but because the planet is following the straightest possible path through curved space-time. From the planet's perspective, it's moving in a straight line. But from our external view, watching through flat space, that line appears curved. This curvature is what we perceive as gravity. And the more massive an object, the deeper the curve it creates. Stars bend space-time more than planets. Galaxy clusters bend it even more. The Great Attractor and the Shapley Supercluster create enormous wells in space-time, curves so deep that galaxies hundreds of millions of light years away feel their influence and begin falling inward. What makes this particularly profound is that space-time curvature doesn't just affect matter, it affects everything, including light itself. Light always travels in straight lines through space-time, but when space-time is curved, those straight lines appear bent to external observers. This effect, called gravitational lensing, has become one of astronomy's most powerful tools. When light from a distant galaxy passes near a massive object, the light's path curves around that object, creating distorted, magnified images. By studying these distortions, astronomers can map the distribution of mass in galaxy clusters, even when most of that mass is invisible dark matter. Gravitational lensing has revealed that dark matter halos extend far beyond the visible galaxies they surround, creating vast regions of curved space-time that shape the motion of everything nearby. The Great Attractor's influence operates through exactly this mechanism. Its enormous mass warps space-time across hundreds of millions of light years, creating a gradient that galaxies follow. We're not being pulled in the Newtonian sense. We're sliding down a curve in space-time, following the geometry carved by concentrated mass. This distinction might seem subtle, but it matters deeply. It means that our motion toward the Great Attractor is not the result of some mysterious attractive force reaching across space. It's the natural consequence of moving through a universe whose geometry is shaped by mass and energy. Every galaxy, every cluster, every concentration of dark matter contributes to this geometry, and the combined effect determines how matter flows across cosmic scales. But here's where it gets even stranger. Space-time curvature doesn't just tell matter how to move. Matter tells space-time how to curve. This feedback loop is at the heart of general relativity. As matter moves and concentrates, it changes the geometry of space-time around it. That changed geometry then influences how other matter moves, which in turn changes the geometry further. Over billions of years, this feedback amplifies small initial differences into the enormous structures we see today. A region that starts out slightly denser than its surroundings curves space-time a bit more. That extra curvature attracts more matter, which increases the curvature, which attracts even more matter. The process is self-reinforcing, turning tiny quantum fluctuations from the early universe into galaxy clusters and superclusters. This is how the Great Attractor formed. It began as a barely perceptible overdensity in the primordial universe, a region where matter was concentrated by just a few parts per 100,000 more than average. But that tiny difference was enough. Gravity began pulling matter toward it, slowly at first, then faster as the concentration grew. Over billions of years, that small seed became a massive structure containing thousands of galaxies, warping space-time so severely that its influence extends across a significant fraction of the observable universe. And the process continues today. The Great Attractor is still growing, still pulling matter toward it, still deepening the curve it creates in space-time. What's remarkable is that this entire process is deterministic. Given the initial conditions of the universe and the laws of physics, everything that follows is inevitable. The formation of the Great Attractor was not random chance. It was written into the distribution of matter from the earliest moments after the Big Bang. Those initial fluctuations, imprinted when the universe was less than a second old, determined where matter would eventually concentrate. Gravity simply spent billions of years revealing what was already encoded in the cosmos. This realization connects the largest structures in existence to the smallest scales of physics. The quantum fluctuations that seeded galaxies and superclusters emerged from processes operating at subatomic scales. The uncertainty principle of quantum mechanics prevents the early universe from being perfectly smooth. Random quantum jitter in energy density created the seeds that gravity would later amplify. In a very real sense, the Great Attractor exists because of quantum mechanics. Understanding this connection requires grappling with one of physics' deepest mysteries: how quantum mechanics and general relativity fit together. These two theories are extraordinarily successful in their respective domains. Quantum mechanics describes the behavior of particles and fields at microscopic scales with astonishing precision. General relativity describes gravity and space-time at cosmic scales with equal accuracy. But they operate on fundamentally different principles, and reconciling them has proven extraordinarily difficult. Quantum mechanics treats space-time as a fixed, unchanging background on which particles and fields evolve. General relativity treats space-time as dynamic, flexible, and responsive to mass and energy. These perspectives are incompatible, and physicists have struggled for decades to find a unified framework that encompasses both. The Great Attractor sits at the intersection of these two frameworks. Its existence depends on quantum fluctuations that occurred when the universe was governed by quantum mechanics. But its current structure and influence are described by general relativity. To fully understand how such structures form, we need a theory of quantum gravity, a framework that describes how space-time itself behaves at quantum scales. Such a theory remains elusive, one of the great unsolved problems in physics. But even without it, we can trace the chain of causation. Quantum fluctuations created density variations. Those variations grew through gravitational instability, described by general relativity. Dark matter provided additional mass that amplified the process. Ordinary matter fell into the wells created by dark matter, forming stars and galaxies. And the result is the cosmic web we observe today, with structures like the Great Attractor serving as nodes where many gravitational flows converge. This history reveals something profound about the universe's nature. The cosmos is not static. It's evolutionary, constantly transforming as gravity reshapes matter across time. The universe we see today looks nothing like the universe 380,000 years after the Big Bang. That early universe was smooth, homogeneous, and utterly featureless compared to the rich structure visible now. Yet the seeds of everything we see today were already present, waiting for gravity to reveal them. In this sense, the Great Attractor is not just a destination, it's a monument to time itself, a structure that took billions of years to assemble, and that will continue evolving for billions more. Every galaxy falling toward it adds to its mass, deepening its gravitational well, extending its influence. The process will continue until dark energy's expansion eventually dominates, preventing new galaxies from joining the cluster. But until that happens, the Great Attractor will keep growing, pulling matter from ever wider regions of space. To understand the Great Attractor, we have to understand how the universe learned to build structures this large in the first place. And that explanation begins not with motion, but with stillness, with a universe so smooth and featureless that structure should never have formed at all. The universe began not with structure, but with near-perfect uniformity. In the moments following the Big Bang, space was filled with a hot, dense plasma, a roiling sea of particles and radiation so energetic that nothing stable could form. Atoms didn't exist. Stars didn't exist. Galaxies were impossible. The universe was smooth, homogeneous, and nearly identical in every direction. As the universe expanded, it cooled. Within minutes, protons and neutrons combined to form the first light atomic nuclei. But it took another 380,000 years for the universe to cool enough that electrons could bind to those nuclei, forming neutral atoms. This moment, called recombination, was pivotal. Before recombination, light couldn't travel far. It scattered constantly off free electrons trapped in a fog-like haze. After recombination, space became transparent. Light could finally travel unimpeded across the cosmos. That light is still with us today. Stretched by cosmic expansion, it has cooled from visible wavelengths into microwaves. We call it the cosmic microwave background, or CMB, and it represents a snapshot of the universe as it appeared 380,000 years after the Big Bang. When astronomers first detected the CMB in the 1960s, they found it was extraordinarily uniform. No matter which direction they looked, the temperature was the same to within a fraction of a degree. This uniformity matched theoretical predictions, but it also presented a mystery. If the universe was that smooth early on, how did galaxies ever form? Gravity amplifies differences. If one region is slightly denser than its surroundings, it pulls in more matter, becoming denser still. Over time, this process turns small variations into galaxies, clusters, and superclusters. But if the early universe was perfectly smooth, there would be nothing for gravity to amplify. No seeds, no starting points. The universe would remain featureless forever. Fortunately, the universe was not perfectly smooth. As instruments improved, astronomers detected tiny temperature fluctuations in the CMB, variations of only a few parts per 100,000. These fluctuations were subtle, but they were real. They represented regions where matter was slightly denser or slightly less dense than average. These tiny differences became the seeds of all cosmic structure. Gravity took those seeds and nurtured them over billions of years. Denser regions attracted more matter. As they grew, their gravity strengthened, pulling in even more material. This feedback loop continued, turning microscopic variations into the galaxies, clusters, and superclusters we see today. The largest structures in the universe, including the Great Attractor and the Shapley supercluster, all began as faint ripples in the density of matter when the universe was less than 400,000 years old. But gravity alone didn't shape these structures. Dark matter played a crucial role. Dark matter does not interact with light. It doesn't emit, absorb, or reflect radiation. We can't see it directly, but we know it exists because we can measure its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain more mass than their stars and gas can account for. Gravitational lensing, the bending of light around massive objects, reveals unseen mass shaping space-time. All of this points to the same conclusion. The universe contains far more matter than we can see. Current estimates suggest that dark matter makes up about 85% of all matter. Ordinary matter, the stuff that forms stars, planets, and people, is a small minority. This ratio matters because dark matter began clumping earlier than ordinary matter. After recombination, ordinary matter was still too hot and too energetic to collapse efficiently. Radiation pressure and thermal motion kept it spread out. But dark matter, which doesn't interact with light, felt no such resistance. It began collapsing under gravity immediately, forming dense halos long before ordinary matter could follow. These dark matter halos became the scaffolding for galaxies. As they grew, they pulled ordinary matter into them. Gas clouds fell into the halos, compressed, and eventually formed stars. Galaxies appeared where dark matter had already carved out gravitational wells. This process didn't happen uniformly. The early density fluctuations in the CMB weren't random noise. They followed patterns determined by the physics of the early universe. Sound waves propagated through the plasma before recombination, creating regions where matter was compressed and regions where it was rarefied. When the universe became transparent, those sound waves froze in place, leaving behind a specific pattern of overdense and underdense regions. Gravity amplified those patterns. The largest overdense regions grew into superclusters. The largest underdense regions became voids, vast empty spaces where galaxies are rare. Over billions of years, matter flowed from voids into filaments, along filaments into clusters, and within clusters into galaxies. The result is the cosmic web we observe today. But this process didn't create isolated structures. It created a hierarchy. Small galaxies merged into larger ones. Galaxy groups combined into clusters. Clusters aggregated into superclusters. Each level of organization reflects billions of years of gravitational evolution. Matter flowing along paths determined by the distribution of dark matter and the initial conditions set during the universe's first moments. The Great Attractor sits at one node of this web. It represents a region where many filaments converge, creating a concentration of mass large enough to influence galaxies hundreds of millions of light years away. The Shapley supercluster, farther along the same direction, is an even larger node. Together, they define a gravitational pathway that the Milky Way is following. This motion is not unique to us. Thousands of galaxies are flowing along the same path, all responding to the same large-scale structures. Simulations of cosmic evolution reproduce this behavior with remarkable accuracy. By inputting the initial density fluctuations measured in the CMB and allowing gravity to operate over billions of years, computers can generate universes that look strikingly similar to our own. The cosmic web appears spontaneously. Superclusters form in the right places. Galaxies move along predictable flows. These simulations confirm that the universe's large-scale structure is not random. It's the inevitable result of gravity acting on the seeds planted during the Big Bang. But simulations also reveal something troubling. The structures they produce match observations only if dark matter exists in the amounts we calculate. Without dark matter, the cosmic web doesn't form. Galaxies don't cluster properly. The universe looks different, smoother, less organized. This agreement is one of the strongest pieces of evidence for dark matter's existence. We may not know what it is, but we know it must be there. Without it, the universe we observe wouldn't exist. Yet even with dark matter, questions remain. Why did the initial density fluctuations have the specific pattern we observe? What set the amplitude of those fluctuations? And why does the universe's expansion accelerate today when gravity should be slowing it down? These questions point toward gaps in our understanding, places where known physics meets unknown phenomena. The Great Attractor and the Shapley Supercluster are not just destinations. They are evidence that the universe began with structure encoded at its birth, structure that gravity has spent billions of years revealing. Evidence that dark matter exists and dominates cosmic evolution. Evidence that the forces shaping the universe operate on scales far larger than anything humans have directly experienced. And evidence that our motion through space is not random. It's directed, purposeful in a physical sense, following pathways carved by the densest concentrations of matter in existence. Understanding these pathways means understanding how the universe itself evolved, and that understanding forces us to confront a possibility, both inspiring and isolating. We are not just moving toward the Great Attractor. We are being swept along in a cosmic current that began before stars existed, that will continue long after the sun dies, and that connects our galaxy to the largest structures in all of existence. The question is no longer just where we're going. It's whether the journey itself reveals something fundamental about the universe's nature, about the forces that govern it, and about our place within a cosmos that is far stranger and far less static than it appears. The universe's motion doesn't end with the Milky Way falling toward the Great Attractor. That motion is part of a much larger pattern, one that connects every galaxy in the observable universe. And understanding that pattern requires stepping back to see the full picture, to recognize that cosmic flows like ours are not isolated events but reflections of the universe's deepest structure. When astronomers map galactic velocities across vast regions of space, they notice something remarkable. Galaxies don't move randomly. Their motions are correlated, organized into coherent flows that span hundreds of millions of light years. These flows trace the gravitational influence of underlying mass concentrations, both visible and invisible. The result is a dynamic, interconnected system where motion in one region influences motion elsewhere. This system is called the cosmic velocity field, and it's one of the most powerful tools we have for understanding the universe's hidden architecture. By measuring how galaxies move, astronomers can infer where mass is concentrated even when that mass can't be seen directly. Dark matter doesn't emit light, but it shapes galactic motion. Superclusters too distant to observe in detail still reveal themselves through the gravitational pull they exert. The cosmic velocity field acts like a map, showing not just where galaxies are, but where they're going and what's pulling them. The Milky Way's motion is one small thread in this vast tapestry. When astronomers account for our motion and map the flows around us, they find that we're part of a much larger structure called Laniakea. The name means immeasurable heaven in Hawaiian, chosen to reflect the structure's enormous scale. Laniakea spans 500 million light years and contains roughly 100,000 galaxies. But Laniakea is not held together by gravity in the way a galaxy cluster is. It's a basin of attraction, a region of space where all galaxies flow toward a common center. That center is the Great Attractor. Everything within Laniakea is being pulled in the same direction, following paths shaped by the distribution of dark matter and the locations of massive galaxy clusters. Mapping Laniakea required analyzing the three-dimensional velocities of thousands of galaxies, a painstaking process that took decades. The result is a portrait of cosmic motion far more complex than simple expansion. Yes, the universe is expanding. Distant galaxies recede from us as space stretches. But that expansion is not smooth. Locally, gravity distorts it, creating flows, attractors, and voids. Galaxies fall into overdense regions, while voids expand faster than average, emptying themselves of matter. This creates a dynamic structure where expansion and gravitational collapse coexist, each dominating at different scales. On small scales, gravity wins. Galaxies cluster. Stars orbit. Planets hold their moons. But on the largest scales, cosmic expansion dominates. Superclusters that aren't gravitationally bound drift apart, isolated by the accelerating expansion of space. The boundary between these regimes is fuzzy, and structures like Laniakea sit near that boundary. We're gravitationally connected to the Great Attractor, but we're also embedded in an expanding universe. The interplay between these forces determines our ultimate fate. But Laniakea is not the only basin of attraction. Beyond its borders, other flows exist, pulling galaxies in different directions. The universe is a patchwork of these basins, each one draining toward its own attractor. And between them lie repellers, regions where galaxies flow away from, emptying space and creating voids. One of the most significant discoveries in recent years is the identification of the dipole repeller, a vast underdense region on the opposite side of the sky from the Great Attractor. This void is pushing us just as the Great Attractor is pulling us. Together they shape our motion, creating a dipole structure in the cosmic velocity field. The discovery of the dipole repeller was profound because it confirmed that cosmic flows aren't just about attraction. Voids play an active role. As they expand, they push galaxies outward, accelerating the flow into nearby overdense regions. This creates a feedback loop where dense regions grow denser and voids grow emptier, amplifying the cosmic web structure over time. The Milky Way's motion is the result of both forces. We're being pulled toward the Great Attractor and the Shapley supercluster, but we're also being pushed away from the dipole repeller. Together, these forces have set us on a trajectory that has persisted for billions of years and will continue for billions more. This dual influence raises a question. If our motion is determined by structures hundreds of millions of light years away, how far does that influence extend? Are there even larger structures beyond what we can currently observe, exerting forces we haven't yet detected? The answer is almost certainly yes. The observable universe has a horizon, a boundary beyond which light hasn't had time to reach us since the Big Bang. But the universe doesn't end at that horizon. It continues, possibly infinitely, filled with galaxies, clusters, and superclusters we will never see. Those structures exert gravitational influence. They pull on the galaxies we can observe, subtly shaping their motion. By measuring these motions carefully, astronomers can infer the existence of mass beyond the observable horizon, a humbling reminder that what we can see is only a fraction of what exists. This realization has led some researchers to propose that the Great Attractor and the Shapley supercluster are themselves being influenced by even larger structures farther away. The cosmic velocity field may extend far beyond Laniakea, connecting our local flow to global patterns that span the entire observable universe. Testing this idea requires mapping galactic velocities at ever greater distances, a challenging task because the farther away a galaxy is, the harder it is to measure its motion accurately. Cosmic expansion redshifts light, making it difficult to separate the galaxy's intrinsic velocity from the velocity due to expansion. But new telescopes and techniques are making progress, and the picture continues to evolve. What we're learning is that the universe is far more interconnected than we once thought. Motion in one region influences motion elsewhere, creating a cosmic web of flows, attractors, and repellers that spans the entire observable universe. The Milky Way's journey toward the Great Attractor is not an isolated phenomenon. It's part of a universal pattern, a symphony of motion conducted by gravity and dark matter. And it forces us to reconsider what it means to say we're moving. We're not traveling through a static, unchanging space. We're embedded in a dynamic, evolving structure where our motion is inseparable from the motions of thousands of other galaxies, all responding to the same underlying forces. This perspective changes how we think about our place in the cosmos. We're not alone in our journey. We're part of a vast, interconnected flow, carried along by forces that began shaping the universe billions of years before the first stars ignited. And that flow is taking us somewhere, toward concentrations of mass so large they dwarf everything we've ever observed. Whether we think of that as a destination, or simply as another waypoint in an eternal journey, depends on how we choose to frame it. But one thing is certain. The universe does not let us stand still. It pulls, pushes, stretches, and compresses, shaping our trajectory in ways we're only beginning to understand. And every new measurement, every refined map, every deeper survey reveals that the forces moving us are even larger, even more complex, and even more fundamental than we imagined. The Great Attractor is not the end of the story. It's barely the beginning, and the farther we look, the more we realize that the universe's motion is not something we observe from a distance. It's something we're immersed in, carried by, and defined by. We are not separate from the cosmic flow. We are part of it, and that realization reframes everything. As our understanding of cosmic motion deepens, another question emerges, one that shifts the focus from where we're going to what happens when structures this massive interact. The Great Attractor, the Shapley Supercluster, and the vast flows pulling us forward are not static monuments. They're active, evolving regions of space where galaxies collide, merge, and transform. And the forces driving these interactions reveal something profound about the universe's ultimate fate. Galaxy clusters are among the most violent environments in the cosmos. Despite their name, clusters are not calm, organized systems. They're gravitational battlegrounds where hundreds or thousands of galaxies orbit a common center of mass, occasionally colliding with one another at speeds measured in thousands of kilometers per second. These collisions are not like car crashes. Galaxies are mostly empty space. Stars are so far apart that when two galaxies merge, individual stars rarely collide. Instead, the galaxies pass through one another, their stars continuing on new orbits shaped by the combined gravitational field. But the gas is different. Galaxies contain vast clouds of hydrogen gas, and when galaxies collide, these clouds do interact. They compress, shock, and heat to millions of degrees, emitting X-rays detectable across intergalactic distances. This superheated gas can be stripped away entirely, leaving the merging galaxies depleted of the raw material needed to form new stars. Over time, repeated collisions and interactions transform spiral galaxies into elliptical galaxies, smooth, featureless structures dominated by old stars. The Great Attractor is filled with such galaxies, the remnants of billions of years of mergers, and the process continues today. New galaxies fall into the cluster, their gas stripped away, their structure disrupted, their futures rewritten by gravity's relentless pull. The Milky Way's eventual entry into this region will subject us to the same forces. As we approach, we'll encounter the hot, diffuse gas that fills the space between galaxies in the cluster. Ram pressure from this gas will strip material from our outer disk. Star formation will decline. Over hundreds of millions of years, the Milky Way will lose its spiral structure, its gas reserves exhausted. Then, as we orbit deeper into the cluster, close encounters with other galaxies will become more likely. Tidal forces will distort our shape. Stars will be flung outward in long streams. Eventually, we may merge with another galaxy, our identity dissolving into a larger structure. This transformation is not unique to the Milky Way. It's happening throughout the universe wherever galaxies cluster. It's a one-way process, a ratchet that turns spirals into ellipticals, young galaxies into old ones, dynamic systems into quiet relics, and it's driven entirely by gravity, the weakest of the fundamental forces, yet the one with the longest reach and the most patient persistence. But there's a twist. While galaxies within clusters merge and evolve, the universe's expansion works against further clustering. Dark energy, the mysterious force driving cosmic acceleration, pushes space apart faster than gravity can pull new galaxies into clusters. Structures that are already bound, like galaxy clusters, remain bound. But structures that are not yet connected will never become connected. They'll drift apart, isolated by the accelerating expansion of space. This creates a stark division in the universe's future. Galaxies within gravitationally bound groups will merge over time, forming larger and larger structures, until only a few massive elliptical galaxies remain in each cluster. But those clusters will become increasingly isolated from one another. The space between them will expand faster than light, making it impossible for signals or matter to cross. Over trillions of years, each galaxy cluster will become a separate, unreachable island in an ever-expanding ocean of darkness. The Milky Way's membership in the local group and its motion toward the Great Attractor determine which island we'll inhabit. We're already gravitationally bound to the structures around us. No amount of cosmic expansion will separate us from them. But galaxies beyond our local supercluster, galaxies we can see today, will fade from view as space stretches the light they emit into undetectable wavelengths. Future observers will see a lonelier universe, one where the night sky contains only the galaxies in their local cluster and nothing beyond. This fate, sometimes called the Big Freeze or heat death, is the current best estimate for the universe's ultimate destiny. Expansion continues forever. Structures grow increasingly isolated. Stars exhaust their fuel. Galaxies fade. Eventually, even black holes evaporate through Hawking radiation, leaving behind a universe of scattered particles drifting through an ever-expanding void. It's a bleak picture, but it's also extraordinarily distant. The timescales involved are measured in trillions of years, far longer than the current age of the universe. For now, the cosmos remains dynamic, filled with structure, motion, and transformation. And our motion toward the great attractor is part of that vibrancy, a sign that the universe is still young enough for gravity to shape its structure. Yet this motion also forces us to confront the limits of knowledge. We can see the great attractor's effects, but we cannot see all of it directly. We can measure the pull of the Shapley's supercluster, but we cannot visit it. We can infer the existence of dark matter and dark energy, but we cannot touch them, manipulate them, or fully understand them. The universe reveals itself to us in pieces, offering clues but withholding certainty. And the deeper we look, the more we realize how much remains unknown. This humility is not a weakness. It's the foundation of scientific progress. Every mystery solved reveals new questions. Every measurement refined exposes new uncertainties. The Great Attractor was discovered because astronomers noticed something they couldn't explain. That unexplained phenomenon became a puzzle, and solving it required new instruments, new techniques, and new ways of thinking. The same process continues today. Dark energy was discovered because the universe's expansion is accelerating when it should be slowing down. Dark matter was inferred because galaxies move in ways ordinary matter cannot explain. Each mystery pushes the boundaries of what we know, forcing us to develop better tools and deeper theories. The Milky Way's motion toward the Great Attractor is one thread in this larger tapestry of discovery. It connects the smallest quantum fluctuations in the early universe to the largest structures in existence. It links our local neighborhood to regions hundreds of millions of light years away. It ties the distant past to the far future, showing how initial conditions, set billions of years ago, continue to shape the cosmos today. And it reminds us that we are not stationary observers. We are participants, moving through a universe that moves with us, shaped by the same forces that shape galaxies, clusters, and the cosmic web itself. That realization is both humbling and empowering. Humbling because it shows how small we are compared to the structures pulling us forward. Empowering because it shows we're connected to those structures, part of a cosmic story that began with the Big Bang and will continue for trillions of years. Whether we think of this motion as falling or flying, being pulled or being carried, the result is the same. We're moving, we're accelerating, and we're heading towards something vast, something we can measure but not fully see. Something that represents both a destination and a deeper mystery. The Great Attractor is not an ending. It's a waypoint, a signpost pointing toward questions we haven't yet learned to ask, and answers we're only beginning to imagine. And the journey itself, the act of moving through space at unimaginable speeds while the universe stretches around us, is a reminder that the cosmos does not sit still. It evolves, transforms, and carries us with it whether we notice or not. For now, the Milky Way continues its journey, 2 million kilometers per hour toward a horizon we cannot fully observe. The stars above us appear fixed, unchanging, eternal, but beneath that illusion, everything is in motion, pulled by forces written into the fabric of space-time itself. And somewhere in the darkness ahead, the Great Attractor waits, patient and inexorable. A monument to gravity's power and the universe's hidden depths. If you found this journey through cosmic motion fascinating, leave a like and subscribe. It truly helps the channel grow. The universe is full of mysteries, and we're just beginning to understand them.